The good news is that people in the aging field for the past 30 to 40 years have developed a series of longevity pathways. And these pathways are illustrated here. This is just a subset of the known longevity pathways in various organisms. And from these longevity pathways, what has been found is that aging/longevity is conserved from yeast to nematodes to flies to mice and to people. And that's my then 4-year-old daughter in the picture. And so what you see is you have pathways like insulin-like signaling, that when you decrease insulin-like signaling, which can't be done in the yeast because it's a single-celled organism, you can increase lifespan in nematodes and in flies and in mice. And there's a lot of good evidence that decreased insulin-like signaling is probably beneficial for human lifespan. Similarly, dietary restriction, which is defined as decrease in nutrient intake without malnutrition, increases lifespan in all of these organisms, and there's good evidence that it'll be helpful in humans. Decreasing the target of rapamycin pathway, similar to decreasing the insulin-like signaling pathway, also is beneficial in lots of organisms. And then a couple additional pathways where increasing Sirtuin activity is beneficial in most organisms, and more recently, decreasing oxygen levels can benefit some organisms. Now, if you look at all of these longevity pathways, there's a single thing that comes to mind that they all share, and that common denominator is stress. What I mean by this is that insulin-like signaling and the target of rapamycin, for example, are pathways who get turned on in good times. And so when the environment is good, when your brain and your other tissues have decided you've got plenty of nutrients, there's no danger that you're under, you're in a situation replete with food, comfortable environment, shelter, etc., you turn up insulin signaling and you turn up mTOR to help grow and reproduce. And the downside of this is it tends to age you faster. Whereas when you have insulin-like signaling decreased in mutations or when times are bad, or when mTOR is decreased when times are bad, this leads to an extension of lifespan because the theory is that the body is hunkering down and preparing for tough times and hoping to wait out till there's better times. Similarly speaking, dietary restriction is a metabolic stress in itself. It turns on a lot of similar pathways, and Sirtuins are also turned on in response to stress, whereas hypoxia is also another stress. And so this common denominator of all these longevity pathways is they either are a stress directly or they turn on stress response pathways. So that brings me to stress response pathways, the idea of hormesis. What doesn't kill you makes you live longer. And so to illustrate what hormesis is, I have this graph here on the right. And the idea behind this is that you have stress on the x-axis, and then you have health or mortality on the y-axis. And the original idea is one of two things would happen. The first is that you have no threshold. You take a stress, and this could be a toxin, this could be an actual physical stress. I don't try to use psychological stress, although that's what people feel a lot, especially during the pandemic. I don't try to use psychological stress here, although it is theoretically possible this would also be involved. And the idea here is if there's no threshold, every extra bit of stress will make health worse and decrease mortality. Now, most stresses are not going to act like this. The assumption was that most stresses would act more like this in red. This is where you have a threshold, where a little bit of stress you can handle. But you get to a point, it's a breaking point, where you cross this threshold, and now you get negative detrimental effects of stress. And this makes a lot of sense. Organisms aren't going to be harmed greatly by any little insult, but if you continue to give insults, you'll end up causing damage. Now, hormesis is what's seen very, very frequently in the lab, and probably in the environment as well. And that's the idea that under stress, organisms actually get healthier under low stress. And so this is called a hormetic effect. And the idea here being that at really low levels of stress, there isn't really much damage, but you still turn on a lot of the stress response, stress protection pathways, which help defend you against future stress or just protect the soma as it is. Now, obviously, if this stress gets too great, you end up in a point where you end up with negative detrimental effects on health and mortality. So these stress response pathways are really important in cellular and systemic maintenance, and they've also been shown to be involved in delayed aging models and to correlate with longevity. And what I mean by that is that organisms with stress response pathways that are more turned on tend to live longer within species, and between species, organisms that are longer lived tend to have better stress resistance. And this makes a lot of sense, since you would never want to make body parts for an organism that's going to live 20 years that only lasts 2 years. And likewise, there's no reason for an organism that lives 2 years to make a body part that's going to last for 20 years if the organism is going to be dead within 2 years. So this is the idea that the stress response, stress resistance, goes along with longevity.